Welcome to this lecture. It's going to be about quality control. When I want to define quality, when I say the word quality, sometimes you might think of good quality and sometimes you might think of bad quality. So there is a degree of excellence of the product or service that we expect. Of course, the expectation is related to the price. So if you pay a huge amount of money for a certain product, so you expect it to have a good quality. So quality is defined as the degree of excellence of a product that fulfills our expectations. Now, the work of the quality engineer involves engineering, and it combines with it statistical process control methods, because the quality engineer aims at improving the quality, gives you a good quality level of a certain product, and at the same time is giving you this quality at a reduced cost. This is done by improving the design and the manufacturing processes. Now, what determines the quality of a product or service? First of all, it is the manufacturing. How do we manufacture this product, or how do we deliver this service? The purchasing is highly related to the quality, because it is the raw material that you purchase. Its quality determines the end product quality. So if I want to have a good quality product, this means that I have to purchase good raw material from the beginning. Then I need to inspect the final product, test it, is it according to the specifications or not. Then how do we do its marketing? How do we do the after-sale service? All this determines the level of quality of a certain product or service. Now, the duties of a quality control engineer, he should be involved in all the production phases, from the design to the testing to getting the raw material, and he also needs to plan the activities related to the maintenance of the product and determining the quality standards for the processes and the material that we're working with. So the quality control engineer determines the standards at which we have to abide by. Also, he determines the sampling procedure. After we finish, let's say, a batch of 50 units of a certain product, how do we determine that this is a good batch? Should we check them one by one, or should we take a sample of 5, let's say? If all the 5 are good and efficient, then all the batch is good or not. So these are decisions taken by the quality control engineer. This is something that you'll have to learn as well, the sampling procedures. How do we do the sampling? What is the number that we take at which sample? Let's say if the first sample was not good, should we throw all the batch, or should we take another sample? So all these things have to be studied. It's part of your work, because the quality control is part of the work of the industrial engineer. So that's why we have to know the reliability of any product, because the reliability refers to the probability that the project will be functional when used. So since any product has certain number of components, then I'll have to make sure that all of these components in my product are functional and will perform as it should do, as intended. So if I want to define reliability of a certain product, I will say that a product that works for a long period of time, it's a reliable one. So this means that all of its components has to be reliable. If the components fail, then the product will fail. So this is also related to probability. There is a chance that this product might fail or not. So reliability is a probability. For example, when I buy a certain product, they tell you that there is a guarantee that this product will not fail before its first year of usage. So I have a guarantee of 1 year. What does it really mean? This means that this product is reliable to be used for 1 year. Now, this company will define the reliability. They will say, for example, we have a reliability of 93% that this product will not fail before the first year. So this percentage, it is a probability, okay? It means that 93% or 93 out of 100 products will function for the first year, and only 7 products will fail before this year. So that's why when we define the reliability, we say it is the probability that the failure of the product will not happen during a particular time. So that's why they will tell you we have a guarantee for 1 year. They are assuming that the product or a certain percentage of the product will not fail during this period. Now, since we know that the reliability of a certain product is highly related to the reliability of its components, we want to see how are these components arranged. Is it in series or in parallel? We have 2 types. Let's begin with the first one, the series arrangement. So when I have components that are arranged in series, the reliability of each component contributes to the quality of the complete product. So the reliability of the system depends on the success of each element in the system. So if product A fails, then all of the system will fail, so the product will stop functioning. This is true for part B and part C. If any one of those components fails, then the whole product will stop functioning. So the equation related for the series reliability is calculated in this way. Reliability of the system is the reliability of A times the reliability of B times reliability of C. Let's say, for example, that I have a computer that has 3 components. The motherboard that has a reliability of 99%. This means that only one product of this category, the motherboard, will fail during a certain period. And we have the hardware with reliability of 90%. Monitor with reliability of 85%. So these are the reliability of each component. Now, what will be the reliability of the computer, the final product? It's going to be the multiplication of the reliability of all of the components. So it's going to be 0.99, which is the 99%, times 0.9 times 0.85. So the overall reliability of the computer is going to be 76%. So that's why the poor monitor and hardware will hurt the reliability of the computer. Now suppose I want to improve the reliability of this computer. So this means that I will improve the reliability of the components. So I'm gonna still use the motherboard with the reliability of 99%, but I will get the hardware with the reliability of 95% and monitor with the reliability of 90%. So let's see what will be the reliability of the computer. It's going to be 99% times 95 times 90. So you see the reliability became 85%. So that's why you should be concerned about the quality of every component, because if one component fails, then the whole system will fail. If the monitor stopped functioning, then you will not be able to use the computer. It will fail. Now with the parallel arrangement, even if I have a failure of one of the components, the whole system will continue to function normally, because the components are arranged in parallel. So this means that we have a backup system. For example, if you look at the lighting system, let's say one of the light bulbs has stopped functioning, you will see that the others will continue to give us light. Why? Because light bulbs are arranged in parallel. Even if one or two of them stop working, the others will continue to function normally. So the reliability of a system whose components are arranged in parallel is calculated in this way. Reliability equals to 1 minus reliability of A times 1 minus reliability of B. So a product with components arranged in parallel will not fail until all the components will fail, and it will function when at least one of the components stay functional. Now suppose that the computer motherboard has two components, A and B, and they are set in parallel. If the reliability of component A is 75% and B is 84%, what will be the reliability of the motherboard? So using this equation, I will say the reliability equals to 1 minus 0.75, which is the reliability of A, multiplied by 1 minus 0.84 reliability of B. So we'll see that the reliability of the motherboard is 96%. As the number of components in parallel increases, you will see that the reliability will increase as well. If you want to compare the reliability of component A alone and B alone, they were less than 96%. Now we still have one type of arrangements which is related to the combination arrangement. You see, most of the complex products, it is a combination of series and parallel arrangements. If you look here at this example, we have part C and part A and B, which are arranged in parallel, and part D. The overall system has to be treated as a series component, but first we will have to finish the parallel arrangement alone, then the output of this parallel arrangement will be considered series with part C and part D. So when I have a combination reliability, I will say it is reliability. It will be represented by RC, combination reliability. It's gonna be the reliability of C times reliability of AB times reliability of D. So overall, it will be considered as a series arrangement, but of course, we have to get the final answer for the reliability A times B, which is parallel. And the final answer, I will put it in series with C and D. It will be more clear using numbers. Suppose here that the computer has three components, the motherboard, which has two components, A with the 75% and B with the 84%. Now it is set in parallel arrangement, and we have the hardware C, which has a reliability of 90%, and the monitor D with a reliability of 85%. This is a combination arrangement. I want to see what will be the reliability of the overall computer. So the first step is dealing with the parallel arrangement. So here I will say that the reliability of the motherboard is, as we saw previously with the parallel arrangement, it is 1 minus the reliability of A times 1 minus the reliability of B. It is still the same example of the motherboard, so we already know that the reliability is 96%. Now I will go back to the system and I will say that the computer's reliability is the reliability of the motherboard times the reliability of the hardware C times the reliability of the monitor D. Now they are all arranged in series, so I will put the final answer for the reliability of the motherboard, which is 96%. So I will say 96% times 90%, which is the reliability of the hardware, times 85% reliability of the monitor. So overall, the reliability of the computer will be 73%. Let's look at this example. Here, I want you to build a product, and we want to test its reliability and cost. Suppose that for building this product we need component A and we need two components of B and they are arranged in series, and we need two components of C to be set in parallel. Now this table will show the reliability of each part. Now we need to design a computer with reliability not less than 88%. So you see we have for component A we have two types with different quality. The first type has a reliability of 99%, however it costs $20. The second type of component A has a lower reliability of 96%, and of course it's gonna have a lower cost. Same with component B. We have two types. One has a reliability of 98% at a price of $150. The second type has a reliability of 94% and a price of $100. Component C, the first type has a reliability of 90% with the price of $30. The second type has a reliability of 95% with a cost of $45. So you see, you will get the chance to choose which type do you want and its related cost. Now, if I want to design this computer that will have one component of A, you will have to choose which type will you want. And I want two components of B. You can choose both components of B to be of type 1 of the 98%, or you can choose one of type 1 and another component B with type 2, or both components B of type 2. Same happens with component C. So you will test those components and the reliability, but I want the reliability of the overall computer not to be less than 88%. So let's suppose I chose one component of A with the reliability of 99%, and I chose two components of B, both of the 98% reliability. And with respect to the component C, I chose both of them to have the reliability of 95%. Now remember, the components C are arranged in parallel. So I want to test the reliability of the computer or the reliability of this combination. With respect to the components of B which are arranged in series, their reliability will be RS. We will represent it with RS. It's related to the series arrangement. It's going to be 0.98 times 0.98, so it's 0.9604. Now, RP, which is arrangement in parallel, I have two C's arranged in parallel. Both have the reliability of 95%. So applying the equation 1 minus 0.95 into 1 minus 0.95 will give me 0.99. Now the combination of the overall system, what do I have? One component of A having 99% reliability. So I will say 0.99. This is related to A. Now the next one is related to 2B, which arranged in series. Now the final answer for the arrangement in series was 0.9604 times what I got from the final answer of the parallel arrangement, which is 0.9975. So you will see that the overall reliability of this combination is 94%, which is greater than the value that I request. Now, what about the cost of the system? Remember that I took one piece of component A at a cost of $20 for the type that had the reliability of 99%. And I chose for B component type 1, which has a cost of $150. And I took two pieces, so I will be paying $300 for component B. And I took two pieces for component C of type 2 at a cost of $45 each. So if I want to calculate the total cost of the components that I took, it will be $20 for A, plus $300 for B, plus $90 for C. So the overall cost of the computer is $410. That's because I chose the components that had the higher reliability and so they had the higher cost. Now, what if I want you to design another system that still had a reliability greater than 88%, but at a cost which is lower than this cost? So this might be a possible question for the final exam, so think about it. Thank you.